Okay, seems like we're live. So we'll get started now. Welcome to the MSI seminar. We're very pleased to have Dr. John Squire from University of Otago in New Zealand, where he's a Rutherford Discovery Fellow, which sets him on a nice track towards the tenure track faculty position there. Jono obtained his bachelor's degree, honors bachelor's degree at University of Otago, where he's at currently now. And then he moved on to Princeton for his master's and PhD in physics, in particular plasma physics, as a Fulbright fellow. And then he moved on to Caltech as a Sherman Fairchild postdoctoral scholar, where we overlapped for about a year. And then having had enough of US, he decided to move back to New Zealand, where he's been there since 2018. So Jono's interests and expertise are extremely broad, as those of you who are attending might have guessed from his talk abstract. He works on general plasma astrophysics and also planet formation, so hydrodynamics, dust gas dynamics, interactions, MHD, and stellar interior protoplanetary disks, stellar winds, the inner cluster medium, the interstellar medium. It's very broad, and it's always a pleasure, and I always learn so much by talking to Jono. So without further ado, please take it away.
Thanks, Eve, and yeah, thanks for coming along. So I guess I should start by pointing out where I actually am, maybe. So that's shown at the bottom here. Most people aren't too familiar with the University of Otago, but it's right down at the bottom of the South Island of New Zealand here. So basically as far away as you can get from you guys, probably. So yeah, as Eve said, I want to talk about kind of a subject that's maybe a little different from most astro colloquia by trying to merge together some of what we know from space physics, so in-situ observations from the Solarwind, with some problems in astrophysics that are interesting. And I probably won't give you too many concrete answers, but hopefully it can be some interesting physics and astrophysics to understand anyway. So just to acknowledge a few of my collaborators, shown down the bottom here, worked on various parts of these projects. Oh, okay, here we go. So before going on in too much detail about the plasma astrophysics side of things, I wanted to start by outlining turbulence as I'm going to kind of use the idea in this talk. So, because I'll be talking a bunch about general problems related to turbulence, because this is how we have to think about energy transfer and heating in this type of plasma. So from this kind of physics perspective, turbulence is the fluid's way to convert the large-scale motions that you stir up into much smaller scale ones that enable energy dissipation. So basically the way we should think of it is that the fluid has a very, very small viscosity. So most fluids around, like air and other things, have really small viscosity. And if we just pushed it, then the amount of energy dissipation that you'd get out of this would be far too small to actually be able to do all that much. We wouldn't be able to dissipate the energy that we put in. So instead, what the fluid decides to do is break up the large scale motions that you create into smaller ones than that. Those break up into smaller ones, et cetera, until you get down to the smallest scales available, where they can actually be dissipated quite quickly. So it's this way of creating fast mixing and fast energy input into the system. So worth noting that if we didn't have turbulence, the really small viscosity would mean that, for example, planes couldn't fly. There wouldn't really be any weather around, because you wouldn't be able to create these motions in the first place. And maybe worst for the physicist, you couldn't stir your coffee, because any attempt to try and mix up the cream would be met with the microphysical viscosity, which would be much too small to allow that to happen. So the turbulence is really this fundamental thing for a lot of different processes. So the standard way that we look at this, you guys have probably heard of, this is Andrei Kolmogorov here. So this is Kolmogorov's law. We want to think of this injection scale, which is where we stir the system up at the start, and then a constant flux of energy through scales. So we create some motions here, they break into smaller ones and smaller ones and smaller ones, which eventually reach the dissipation scale. And through this range called the inertial range, there's a constant flux of energy. So keep in that mind this idea of energy moving towards smaller and smaller scales and being approximately constant as it does so. So it's often said that turbulence is like the biggest unsolved problem in classical physics. But I guess it's worth clarifying what we're even trying to solve if we say that. So I'll just get my spotlight thingy. In a way, there's two parts to this problem. And the first would be some sort of thermodynamics thing. So I said that turbulence is a problem of energy transfer. So we can ask, how is the fluid actually going to be heated when we do this work on it? So we stir it up. How is it heated? So in a neutral gas, like I showed before, this is actually a pretty easy problem because all that energy that you stir up eventually goes into heat. And so we basically know what happens. It's just the heat capacity. But the other question that involves solving turbulence is the structure. So this is, what does the fluid do when we move it around? So there's some sort of statistical description of the eddies and how they move. So for example, the Kolmogorov law says that the relative size of the velocity between 2 points separated by length scale L scales as L to the 1/3. So that kind of theory, but then it gets much harder with intermittency and everything. So this part of solving turbulence is very hard, even in a neutral fluid. Okay, so that's kind of my description of the basic ideas of turbulence. But of course, many of the plasmas or gas in general that we see in astrophysics is weakly collisional. So what I mean by this is just that they support and we observe motions in the fluid on scales much below the mean free path between particle collisions. So a really simple, though flawed measure of this would be something like the mean free path divided by the gyro radius, the ion gyro radius in the system. And so you can see how this scales here. Particularly notice that there's a pretty strong power of the temperature. So a hotter, more diffuse plasma is going to be much less collisional. I should clarify that a big number here means that it's very collisionless or weakly collisional. So a few examples we're probably familiar with. The intracluster medium is maybe the nicest example of this type of plasma, seen here in the X-ray. The interesting thing about this is that we can actually measure motions, observe motions below the mean free path in the intracluster medium now. So we're really probing these systems in quite a bit of detail. High energy accretion, so around black holes and other things is in this regime, and I'll come back to this in a moment. And then regions of the ISM, such as the warm, particularly the warm ionized or the hot ISM, are pretty well in this regime as well. So just some ideas to keep in mind as we go forward. But what does it actually mean that what does it mean that it's weakly collisional or collisionless? What are the implications? Well, the first and kind of most obvious one is that we shouldn't really use fluid equations to describe it. So things like magnetohydrodynamics or MHD, that's not really allowed. Or if we can use these, and we often can, and it's sort of okay, do we get the right answer? We probably miss some things that we should keep, really. Then the heating, going back to this sort of really basic question of how much energy goes into different channels, ions, electrons, and other things aren't actually coupled together. So they can have different temperatures and different heating rates. And then the temperature itself is not even necessarily well defined. So for example, you can get a thermal speed that depends on the direction in the plasma. Particles might be going faster in one direction than another. And then you can get things like particle acceleration and other non-thermal distributions. And then sort of most philosophically, why are the motions even supported at all? So in a neutral gas, if we try and ask what happens below the mean free path, so in this weakly collisional regime, we'll find that there isn't really anything at all. If we try and create a motion, it immediately gets damped out because a particle will just go from one place to the other immediately and transfer all that momentum, and you can't really create motion, so it doesn't even really make sense to talk about this. But in a plasma, of course, we have the magnetic field that confines the particles perpendicular. So we can get all of these interesting dynamics on scales much below the mean free path. Okay, so let's go back to this question of what we're trying to solve before coming to some of the astrophysics of this. What are the answers that we're actually trying to solve about say, turbulence in these weakly collisional plasmas, or more generally just their motions. So again, break it into thermodynamics and structure. So the thermodynamics, how does the energy transfer and the heating work? Well, this has become much more interesting than in the neutral fluid case now, because we don't have to have the same amount of energy reaching ions and electrons. And this can have important consequences for observations of things or other stuff. And then even this heating ratio between the ions and electrons can actually depend on how you stir the system or the plasma parameters in ways that's really not obvious. And then we have things like non-thermal distribution. So this problem that was easy before has become quite hard. The structure is relatively similar before, but still pretty hard. So the most obvious question, is MHD a reasonable model to use? Can we still apply things like Kolmogorov's ideas and other stuff? But we want to know aspects of how this works, and it's just as hard as before. So a more complicated problem than neutral fluid turbulence, and I think a lot more interesting in various ways. So before going on to kind of explain some of the results that we know about and things that we've been working on recently, I thought it would be helpful to put some of this in context of some problems in astrophysics which require pretty detailed knowledge of how these processes work. So the first example is going to be radially inefficient accretion flows, which is pretty topical with the Nobel Prize today. And then the second example is cosmic ray propagation. So this first example is mostly going to be to do with thermodynamics of the turbulent and energy transfer processes, while the second one is mostly about the structure that comes along. And what I really want to argue is that the relatively detailed knowledge of how the plasma behaves is quite important for really bulk properties of these systems. So first to talk about radially inefficient accretion. So these are basically extreme 2-temperature plasmas around black holes or potentially other compact objects. So here's a beautiful image from the Event Horizon Telescope last year showing M87, which is in this kind of state. So effectively the system can't easily radiate away all of its energy. And so because of that, the energy builds up and it forms a very, very hot disk around itself, which puffs up and becomes what's often called a radially inefficient accretion flow. So most models of this, if you go into a bit more detail, require that the ions be preferentially heated to the electrons in order to be stable. So in the system, if you want to actually construct one of these that works, you need to heat the ions. The plasma needs to naturally heat the ions more than the electrons. And then we also, the electron temperature being much less than the ion temperature is also consistent with observations. And more generally, it's just this ratio of ion to electron heating is a really important parameter in constructing these types of things and in understanding what observations of things like M87 actually tell us. So the kind of natural question that comes out of this from the basic physics standpoint is this actually allowed by the plasma? So that is, if we stir it up, what is the ion heating rate, QI, over the electron heating rate, QE, and how does this depend on other parameters like the temperature ratio and other things? So we plug in some fluctuations, we get some turbulence or other things. Some of that energy goes to ions, some goes to electrons, some non-thermal particles. How is this distributed? And the kind of interesting thing about this problem is that if this answer is not 1, or if it doesn't tend to 1 in certain limits, then this is kind of like violation of the second law of thermodynamics. The reason being that we've got random and chaotic fluctuations in the system that won't lead towards thermal equilibrium. In other words, they won't lead to the ions and electrons having the same temperature. And if that's the case, that's really one of the very few examples from physics that we know of where this actually happens. So does that happen, I guess, is the first question. And the answer seems to be yes, which is, yeah, kind of weird. So there's been quite a bit of work on this recently, just the last year or two, probably partly motivated by Event Horizon Telescope and other things. So this left panel here shows some simulations from Vladimir Zdankin, where they actually include the electron cooling properly. And this is showing the ratio of the ion temperature over the electron temperature as a function of time. And you see that it just continuously increases. So this black line here shows that ratio. And then they start from a really extreme plasma here with the green line and keep going, and you can see that it increases even more. So basically, there doesn't seem to be any obvious limit on this ion to electron heating ratio in sort of pseudo violation of this second law. So there's some more idealized simulations I've shown over here on the right from Yohei Karazura. So the important thing here is he's studying this heating ratio as a function of the ion temperature divided by the electron temperature. So if it was wanting to get back towards equilibrium, you would expect that the heating ratio should increase as this thing increased so that it pushed itself back towards equilibrium. But it seems to be completely independent, so it has no tendency to do so. So just to point out for later, the blue lines here are when it's a very strongly magnetized plasma. And I'll come back to what that means in a moment. And the ones up here are when it's weakly magnetized. So you can see that this heating ratio depends on the plasma parameters and properties in kind of important ways. The other weird thing about this problem is it seems to depend reasonably sensitively on how you actually stir the system. So this would be like if you took your coffee and you stirred it in one direction rather than completely randomly, you would get a different answer. You'd heat ions rather than electrons or vice versa. So this is kind of a bit of a bizarre behavior that I don't think has any analog in things we're used to on Earth. Just as a quick example, the plot on the left here shows what happens if you drive sound waves through the system instead, in which case it heats ions. And then I'll come back to this other one later, but this is like if you're stirring in a circle rather than completely randomly, you find that you heat ions as well. So sort of bizarre behavior. But overall, the general idea is that nearly always across most parameter regimes and different things, ions are heated more than electrons in these plasmas. And this is good for these radiatively inefficient accretion flow models. Okay, so the second example I want to talk about is cosmic ray propagation. And this one's more about the structure that develops in the turbulence. So as we stir up these motions at large scales, how do they develop as they get to smaller scales, and what kind of shapes do they make in space? So the reason this is important for cosmic rays, we measure most of the energy in cosmic rays is contained in those nucleons with approximately a GeV energy. So these are the highest energy density ones. So they're going to have the strongest influence on things like galaxy formation, the ISM. But we measure these to be very isotropic at Earth, which means they must diffuse around the galaxy. They must scatter off stuff. Otherwise, we would see them coming from particular sources. And we know basically by process of elimination that this has to be magnetic irregularities. So they're streaming along the magnetic field, then they hit a little bump and they scatter off. And these bumps has to have scales of order the gyro radius to be efficient at scattering. So this tells us that what we care about for this problem is sub-AU bumps in the magnetic field that might be able to scatter cosmic rays. So the question is, where do these sub-AU bumps come from and what's their structure so that we can understand how cosmic rays propagate? So there's a couple of main scenarios for how this can work, usually broken into extrinsic scattering and self-confinement. So extrinsic scattering is just what it sounds like. We have some pre-existing fluctuations in the system from being stirred up at large scales, and the cosmic rays hit them and bounce off, basically. And this ends up having a strong dependence on eddy shape, so the shape of the turbulence that comes along, and I'll come back to this in a moment. The other scenario is called self-confinement. So this is as the cosmic rays move forward, they are strong enough to excite the magnetic field and change its properties themselves, and then they scatter off those things that they create. And this also has a strong dependence on the properties of the plasma, because it turns out to depend a lot on how the magnetic field fluctuations are damped and other things. So we really have to worry about kind of the details of what these do. Just as a quick example of sort of why we have to worry about these details, if we go through, for example, the extrinsic turbulent case and think about what numbers we get out when we plug in slightly different assumptions about the turbulence. So if we assume everything is isotropic, so basically following that Kolmogorov law I mentioned before, you'll find something 10 to the 29-ish. So the number here is not super important, but it's just, we'll compare the magnitudes and different assumptions. So that was the isotropic case. if we instead correctly account for the eddy elongation along the magnetic field, you can estimate that you'll actually get something about 6 orders of magnitude bigger for this diffusion coefficient. So this would have very different consequences, for instance, on how the cosmic rays influence the ISM and how we measure them at Earth. And then if we as well included things like sound waves in the model, and this is pretty iffy on how you're supposed to do it, but if you do that, you'll find, again, a much smaller number. So basically the point here is not that one of these is correct over the other, but that we have pretty large leeway in well, the scattering coefficient, which is a kind of global bulk property, depends in quite a bit of detail on the sort of seemingly esoteric details of the turbulence itself. So it turns out there are similar uncertainties with the self-confinement scenarios. And then this has been something that we studied recently with Phil Hopkins using cosmological simulations and trying to compare with observations of gamma ray luminosity from galaxies, which give an indication of how many cosmic rays are in the halos. So what he found, or what we found, was that these extrinsic turbulence scenarios seem to produce too little confinement. So the black dots over here, these are measured galaxies, and the colors are different cosmological simulations. It seems to match the red one reasonably well, but this is one of these models that isn't actually physically well motivated. And then the self-confinement ones kind of do the opposite. They produce too much confinement. So you can see it sort of matches the green, but this green one has just been artificially enhanced by a factor of 50. So the point of showing this is to say that we still really don't understand how these processes work, this cosmic ray scattering and confinement. And it all depends in kind of detail on the physics of this hot gas. So I should just also point out that one of the other findings of this work was that the weakly collision, also the hot and the warm ISM, were the really controlling factors for the cosmic ray confinement rather than the colder neutral gas. So that brings me now back to my title, I guess, which is kind of nicely summarized by this review article here, the Solarwind as a Turbulence Laboratory from Bruno and Capone. So basically the Solarwind is a well-designed wind tunnel for studying these types of problems, or in general, plasma turbulence and plasma fluctuations. So the reason I say that, it's obviously the solar wind is a fast wind coming off the sun, which streams past Earth. The mean free path is approximately an AU in the solar wind. So it's a very much in this weakly collision or collisionless regime. And then because it moves so fast outwards, if we put a spacecraft somewhere in it, then the temporal fluctuations that we measure, so like you get some time series of magnetic fields shown here, can be converted directly into the spatial fluctuations in the plasma. So you can basically think of any measurement of the time changes in the plasma as just being directly convertible into space. So this is really convenient for doing things like measuring how the turbulence works. So here is a really beautiful spectrum put together by Chiani et al. So this is showing the relative power in magnetic fluctuations as a function basically of scale along the x-axis. So really small scales down here, really large scales down here. And by some definitions, this is the widest turbulence spectrum we measure anywhere. So either on Earth or in other scenarios. And it's really, really high quality data because it's measured in situ rather than using external observations. So just a few things that we can learn from this. Going back to that heating question, how much power goes to ions and electrons? We think that this is determined around the scales here. So this is the ion gyroradius, and that's because some of the energy will make it, some of the energy makes it through the scale and goes on to heat electrons, and some of it doesn't and heats ions. So we can measure the properties there. Then also those compressive motions that I talk about can do a bit of heating at the outer scale, and we can measure those properties. The GeV cosmic rays are sensitive to the effective scale in this kind of middle range here. So this is if we translated the solar wind into, say, the ISM, and we can measure the shape of these eddies with very, very good detail. So that's shown here on the left. This is just shown if you measure it in the parallel direction in blue compared to the perpendicular direction in red, you find that these eddies are really, really elongated along the magnetic field. So it tells us that, say, that first scenario of the cosmic ray scattering is not correct. So we can measure these things in detail. An important parameter here, which I just want to highlight because I'll be using it quite a bit as we go on in the talk, is called the plasma beta. So this is the thermal pressure in the plasma divided by the magnetic pressure. So this might seem a bit backwards from the astrophysics standpoint because a low beta plasma is very strongly influenced by the magnetic field. The reason this is backwards is because it was originally defined in fusion physics, where they naturally don't have much plasma but have a strong magnetic field. So that's why it's a bit confusing. But basically, yeah, low beta plasma means it's very strongly magnetized, which means particles move slowly compared to the magnetic field perturbations and things. So this will apply to coronae, jets, experiments here on Earth, a bunch of other things. Beta larger than 1 is the opposite regime, so weakly magnetized, meaning particles move fast compared to B. So this applies to like the intracluster medium or disks and other things. So what we're seeing here down in this plot is the distribution of beta measured in the solar wind. So forget about the y-axis for the moment, we'll come back to that. But you can see that most of the data is centered around beta of 1 or so, but it extends really far outwards in both directions. So this is pretty convenient too, because we can measure how the properties of the plasma change as a function of this really important parameter by kind of isolating this region for low beta or this region for high beta. And there are new spacecraft going up all the time, which are making new high quality measurements from different regions. Like Parker Solar Probe, launched just less than a couple of years ago, is going as close to the sun as we've ever been and making some really beautiful measurements of the, not quite the corona, but getting pretty close, the near sun solar wind. Okay, so let's recap some of what I've said so far and then give an outline for what I'm going to talk about in the rest of the talk. So one key point was that the turbulence controls the thermodynamics. So if we want to understand heating of any plasma which is weakly collisional or collisionless, we have to understand the turbulence because it's all controlled by that, and you get different answers depending on different properties of that. The structure that develops is also important for problems like cosmic ray scattering or magnetic field generation or other things. And then the main point from this last part was just that we have these beautiful measurements from the solar wind, so we can use them to test and understand our theories and see if we understand what's going on. The answer is usually no, but it usually yields some interesting insights. So for the rest of the talk, what I want to do is go through some of the results that we've been working on recently in a couple of different regimes, and just to give you a flavor for some of the weird things that these plasmas do and how these might influence astrophysical problems. So I'm first going to talk about high beta plasmas. So these are the weakly magnetized ones. And the story here is that the plasma makes its own collisionality. So it's collisionless to start with, but it basically manufactures its own collisionality by making small scale magnetic perturbations. And then I'll talk later quickly about some really recent work in the low beta regime. And this is the story here, is basically how the plasma stops heating itself altogether by stopping the turbulent cascade.
John,
Okay.
before you move on, there was a question in the Slack channel.
Oh, I don't have the Slack channel, sorry.
Oh, you wouldn't know. That's why I'm here. So the question is in relation to where you compare the confinement of cosmic rays. You showed this two plots from the paper with Phil Hawkins.
Yeah.
So why is the number of galaxies used so limited, and where do the large discrepancies of the far galaxies emerge?
So these are the ones, oh, sorry. Sorry, there we go. So these ones there. So the number of galaxies is limited because we don't have particularly good gamma ray observations from so many of them. So is that these ones up here? Is that what we're asking?
Yeah. So I had a quick question about this graph, which was, why was the number of galaxies? What was the limiting factor in the number of galaxies in the study, and then why were there large discrepancies in the further galaxies? Because it seems like each one of those different galaxies is preferring a different model.
so just the scatter here. So this is a plot of the central density in the galaxy, and these ones up here are starburst models, starburst galaxies, sorry. So that's the discrepancy along this line. I think one of these two here are the LMC and the SMC, and we're actually not entirely sure why they have such low gamma rays luminosity, but it's probably due to differences in things like the metallicity and other properties, but we're really not too sure. As for why there are so few, I think it's just that there are these observations of the gamma ray luminosity from the halos are quite difficult, so we don't have all that many as of yet, that's all. Does that answer your questions?
Yeah, thank you.
Sure. Okay. All right, so I want to go on to talk about these different, this high beta regime now. So this is when it's weakly magnetized. And as I said, the story is basically the plasma making its own collisionality. And a key concept here is going to be this thing called the pressure anisotropy. So the idea is just that since we're collisionless, there's nothing to isotropize the motions. So it means that particles can, on average, move faster around the magnetic field than they move along it. So this is then called a pressure anisotropy if this happens. So just to give an idea of what this looks like, if we think about the distribution of particles in V parallel and V perp, then if the pressure anisotropy is bigger than 0, this distribution looks a bit like a pancake because they're going faster around the field than along the field. If the pressure anisotropy is less than 0, it looks a bit more like a football because the particles are going along the field faster than they're going around the field. So a reasonably simple concept, relies on the lack of collisionality because otherwise these become isotropized with each other. So there's two key properties of this pressure anisotropy that we have to worry about for figuring out its influence. So the first is that it's created whenever the magnetic field changes. So those of you who've taken a plasma physics course will remember that this thing here is called the first adiabatic invariant, and that's approximately conserved. So since V perp squared is basically the perpendicular pressure, we can see that if magnetic field goes up, this is the magnetic field strength, then the perpendicular pressure goes up, which means the pressure anisotropy goes up. Whereas if B goes down, the pressure anisotropy goes down. So it's basically tied to changes in the magnetic field strength in the plasma. The second key property is that it exerts a force on the plasma flow. So it modifies the magnetic tension. So just to kind of show what that looks like, in standard MHD, you have the acceleration of a particle of fluid or plasma, looks like this. It's got some other stuff, but then this is the magnetic tension term. So this is basically when I bend the magnetic field line, it wants to bounce back. If I add in a pressure anisotropy, I just get this. So I've added in this extra term here. So this is another force on the plasma that comes from this pressure anisotropy that can change what it does, basically. Changes how it behaves when you push it. So if we go through what these properties mean, property 1 says that the relative size of the pressure anisotropy that you get from a perturbation to the magnetic field strength scales as beta, basically. So as beta is bigger, we're going to get bigger changes to this pressure anisotropy. Then we plug this idea into property 2, that force. And what we find is that this normal term, the normal magnetic tension term, is quite small, whereas the new term is really big. So in other words, we've added a new term into MHD and decided that actually this new term should be much more important than the one we usually think about. Another way to put this is that the momentum stress due to this pressure anisotropy scales as about beta times the magnetic forces. So we shouldn't ignore it, in other words, it's pretty big. And yet another way, if we make tiny changes to the magnetic field strength in this type of plasma, it's going to cause really big changes to what the plasma does. So any really, really small perturbation causes a big effect. And we can see that this happens whenever the magnitude of the pressure anisotropy is about magnetic field strength divided by 4 pi. And that's just from when this term changes by a lot. And it's very easy to reach at high beta. So if we go into the solar wind and we try and measure this type of property, this pressure anisotropy, you get something like this. So this is a really nice plot from Stuart Bale, which shows as a function of beta and pressure anisotropy on the x-axis, scaled slightly differently, but same idea. He's basically taken each of these intervals at a given parameter set and then asked how many fluctuations there are in the plasma can we measure at small scales. And so the color shows the magnitude of these fluctuations. So these lines where the pressure anisotropy is big compared to B squared are these ones, these dashed lines here. And you can see that around those lines, we get a lot more small scale fluctuation in the plasma. And these are called microinstabilities. So it's basically the plasma making itself unstable and growing lots of small scale stuff. And the point to point out here is that the intracluster medium and disks and other things live far down the right of this plot, which means that any tiny little perturbation to the system is going to cause it to push over these limits and grow these things. So the kind of conclusion here is that the plasma is making its own collisionality, and it's always going to be in this unstable state. So we've explored this a little bit with simulations, which I'll show here. So the top simulation shows what happens if we push the perpendicular motion in the plasma, so an Alfvén wave, for those familiar, whereas the bottom ones show what happens if we make a sound wave. So this is an initial density perturbation. So what we're going to see is that we'll get a really slow change to the magnetic field at first from these large scales changing, and then it will push the pressure anisotropy over the limits, at which point the plasma erupts in a whole bunch of stuff. And these are the microinstabilities, and their effect is to scatter particles. So this top one is showing the magnetic field. It's a sine wave to start with, as you can see. So if I start the video, you can see that we grow all this stuff suddenly. So these are those microinstabilities that we were seeing in that previous plot of the solar wind, now just in a simulation. And the general effect here is that these things end up scattering ions. So if you think of an ion going along happily in the magnetic field and then suddenly smacking into one of these little perturbations, it's going to hit it and scatter off. And this behaves a bit like a collisionality in the system. So it was collisionless, but now we've added in collisions because the plasma's created them itself. The same sort of thing happens with the sound wave. So this is just showing different components of the magnetic field here from an initial density perturbation. And you can see that it just goes all sorts of crazy, basically. So the idea here is that if we could actually make, say, an image of the solar wind, or if even better, we could take a look in detail at the intracluster medium, what we would see is not a smooth plasma, but one that was filled with all these fluctuations all over the place that were bouncing off particles. And so any idea of a smooth high beta plasma doesn't even really make sense. So this gives us kind of a modified picture of what turbulence should look like in the system. So before I talked about how we stir up stuff at large scales, and they make smaller scale things and smaller scale things until they reach the smallest. But now we have this way of jumping from the large to the small. If we make a reasonably sized perturbation, we go over those pressure anisotropy limits. They immediately create microinstabilities, which can then dissipate energy straight away. So it kind of changes the general picture of how all this works. So if we again break this into the thermodynamics and the structure, so we'll see that the thermodynamics should actually be controlled mostly by how these microinstabilities behave. And they then depend on things like beta and the temperature ratio and other things. So just as an example, this is some nice work by Lorenzo Cerrone from Columbia, showing how the instabilities can look a bit different depending on the ion to electron temperature ratio. And then you can also get different heating rates. But I guess the general point is that because the instabilities grow on the ions, almost all of the heat that you inject in the first place is going to go into ion heating, very, very little electron heating. The structure is also modified by the pressure anisotropy. Basically what happens is that the large amplitude motions behave differently to the small amplitude ones because the large amplitude ones create this pressure anisotropy. So it gets a little weird and confusing, but just to point out, the perpendicular motions, so like the top video I showed, end up having more damping than if they were in an MHD or a low beta plasma. And that's just because this modified magnetic tension term goes to 0. Whereas the parallel, so the compressive ones, like the bottom videos I showed, have less damping. And that's just because they create this collisionality that then shuts off the damping mechanisms. So to show that we can measure this stuff in the solar wind, this is showing how the perpendicular fluctuations, when they're large amplitude above this line, a prediction is that it will be left with magnetic stuff and no velocity stuff. And you can see that we actually measure this. So we can know, at least to some degree, that these these predictions are borne out in a real system and apply them to things like cosmic ray scattering. And then the compressive fluctuations are also more like MHD. So this is some really nice work by Daniel Vacharin. They measured properties like the density divided by the magnetic field strength and the parallel velocity divided by the magnetic field strength, and then plotted these on a histogram again. And they found that all the data basically lied perfectly along the line that it should if it was a standard collisional plasma. So this is saying, even though the plasma is actually collisionless, when we make these measurements, it lies perfectly along these lines, which makes it look like a collisional one. So we think that this is these microinstabilities turning our collisionless plasma into a collisionless one. So slightly weird behavior. So a quick summary of how the high beta case works. The key idea here is that the plasma makes its own collisionality from these microinstabilities. So it's never going to be truly collisionless. And this will change things like the structure, but basically because you need such small perturbations to do so, this type of plasma is always going to be filled with this kind of magnetic noise shown here in the video. And it's almost all ion heating, probably larger than 90% in these plasmas, which is good for these models like radiatively inefficient accretion flows. Okay, so now I want to go on to the low beta regime just for 5 minutes or so and talk about how some really weird behavior in this plasma is that it actually stops heating itself. So it turns off its turbulent cascade altogether. So this is the regime, to go back to that plot of the pressure anisotropy from before. We're on the far left. And so you can see that you need a big push in either direction to get to those limits where the pressure anisotropy becomes important. So we don't think it's so important in this regime, but we can still ask that question. If we stir things up, how does the energy partition between ions and electrons and maybe fast particles? And this is kind of what I'll be exploring for this final part of the talk. So if we go back to this picture, this really nice spectrum from Kiani et al., we think, as I said before, that this question is mostly determined by what happens at the ion gyroscale. So that's here, the size of the ion gyroradius. So fluctuations that are about the size of the ion gyroradius. So it's determined because some of the power in the electromagnetic fluctuations, which is supposed to be this, which is this gray, signified by the gray stuff, will make it through the ion gyroradius. And if it makes it through, then it can go to smaller and smaller scales and heat electrons. And the standard story is that at low beta, so in this strongly magnetized regime, most of the electromagnetic energy can get through. So it goes through the ion gyroradius, goes to really small scales and heats the electrons. So what we've shown recently, though, is that this depends quite sensitively on how you stir the system, which is a bit weird. So I made this analogy with a coffee cup before. It would be like a different type of stirring, changing how much you heat the system and how you heat it. So there's kind of 3 ways we can think of doing it for this plasma case. The first case is called balanced. So this is as if we just randomly stirred it in all directions at once. The second one that I'll talk about is called imbalanced. So this is as if we took our spoon and stirred all in the same direction instead. And then finally compressive, which is as if we drove sound waves through the system or something like that, which is a bit harder to do perhaps with a coffee cup. So it turns out that the solar wind itself is mostly in this imbalanced state, which makes sense because the fluctuations are created by the sun itself, and so they mostly propagate outwards. And so when we measure it, as shown here, we see that most of the fluctuations are propagating outwards, and there's only a small component of inwards propagating fluctuations. So what really weird thing happens is that when you have this imbalanced situation, so most stuff propagating in the outwards direction, you end up stopping the turbulent cascade altogether. So to show what this looks like, it's best to start by showing what the normal case looks like, which is shown here. So as I said, most of the heating goes to electrons. So our electromagnetic energy goes all the way down, goes through the ion gyroscale, and then goes to the smallest scales. And we can actually plot the energy flux from simulations. So this is the energy going through each scale. And it looks pretty flat, as you'd expect, because there's nothing too crazy happening. It all just goes straight through the ion gyroscale and down to heat electrons. If instead we force imbalance, then it changes completely. So the energy flux now looks like this. It builds up at larger and larger scales in time and fluctuates around wildly. And what's actually happening here is that the energy that wants to go to the smaller scales instead hits this thing called the helicity barrier and then bounces off and comes back to large scales. So this is kind of weird behavior because it means that the plasma actually can't heat anymore. Instead, the electromagnetic fluctuations just get bigger and bigger in time. So what causes this? So the first point is that at low beta, remember I said the magnetic stuff moves faster than the particles at low beta. So this means that you can't transfer your electromagnetic energy into ions because the ions move too slowly. So there's this kind of insulation between the electromagnetic stuff and the plasma particles. And then the second cause is there's an extra conserved quantity, the helicity, which undergoes a forward cascade, so meaning it moves to small scales when you're at bigger scales. But if you're at small scales already and you try and excite helicity, it wants to move to bigger scales. So that's called an inverse cascade. And this is like what happens in two-dimensional turbulence, for those familiar with that. So the outcome of this is that the two basically collide together. The forward cascade hits the inverse cascade and it forms this helicity barrier. So the result of this is that, as I said, rather than heating the thing at all, it just grows the electromagnetic energy in time because those fluctuations can't do any heating. And what we get is these really steep spectral transition ranges, which really matches quite nicely what's observed in the solar wind. So this is showing some really recent work from the Parker Solar Probe spacecraft. You can see this is the large stuff, then it gets really steep for a while. This is a spectrum, and then it flattens off again. And then from our simulations, we see exactly the same thing. It's flat for a while, it gets really steep, and then it flattens off again. And this really steep region is due to this helicity barrier. So the turbulent energy can't keep growing forever. So this thing gets bigger and bigger in time until eventually it's going to start heating ions. So that's different from the standard scenario. Oh yeah, so just to compare this imbalanced one to the balanced one, you see that they look quite different. So we can distinguish between these scenarios in the solar wind and use that data to understand whether we're correct. So just as a pretty picture, this is again showing the difference between the balanced and the imbalanced case. Balanced looks like this, imbalanced like this. So you can see they look completely different because of this helicity barrier. So a quick summary of this low beta regime. As I said, under highly idealized conditions, you can heat electrons, and that's shown here on this plot. Qi over Qe at low beta is mostly heating electrons because it's small. But we showed that this depends quite strongly on how you stir the system, which is quite different from things like a coffee cup. So if we're imbalanced, you get this helicity barrier, you heat ions. If you're compressive, you also heat ions, as shown by this plot here. It gets more compressive as we go right, and we get more heating. And then even if you're less ideal, you also heat ions. So the general story here is that basically any plasma, you end up heating the ions more than the electrons in violation of the second law of thermodynamics. So just a few conclusions. Kind of the basic takeaway of the talk is that we can measure the properties of the collisionless plasma from the solar wind, and it's really this perfectly designed wind tunnel to make measurements of these things that can also be quite interesting for astrophysics. I talked about thermodynamics and structure. So thermodynamics is basically how stuff is heated, electrons and ions, the bulk properties of the plasma. And unlike in a neutral gas, we actually have to worry about turbulence in some detail to understand the thermodynamics of the system. In the weakly magnetized, so high beta case, we saw that the plasma made its own collisionality, so it didn't really like being a collisionless plasma, it manufactured its own. And then in the low beta case, we had these weird surprises from the helicity barrier. And then we also talked a bit about the structure. So this is things like the eddy shape, the magnetic or velocity spectra, the types of motions that are actually possible to propagate. And it can be quite important for things like cosmic ray propagation or interpreting observations of scintillation or magnetic field growth in the ISM. And we can again make pretty detailed measurements of this from fluctuations in the solar wind. So thanks, that's all I've got.
Okay, great. Thanks, Jono, for the very nice talk. So questions, you can continue putting your questions on Slack, or you can raise your hand on Zoom, and I'll just call you up. Jordan?
Hey, yeah. So this is getting back to the very beginning of your talk about the accretion flow around Sagittarius star. And maybe you said this and I just missed it, but could you comment on the ability of these models to provide some kind of intuition for the variability in the accretion flow that's been seen in various monitoring campaigns over the last 10 or 20 years?
Yeah, I mean, a little bit. I'm not super expert on the details here. So I think that their full general relativistic MHD models can account for some of this in reasonable detail. At least that's my understanding. So they basically run these pretty complicated 3D accretion flow models and then try and map the radiative transfer and things to measure to see what an image will actually look like. And I believe it shows reasonable agreement to the variability they see, though someone should feel free to correct me if I'm wrong. I guess the point from the basic plasma standpoint in this is that they actually use these types of heating models and the turbulence models as an input to those GRMHD models. And it's kind of just at the moment a bit of an unconstrained knob to turn for the most part. So trying to constrain that is sort of I guess there are multiple levels of how you want to do it. The more realistic models require these kind of simplified things as an input to be able to actually make those predictions of, say, the variability of the accretion itself and stuff. So, yeah,
thanks. That's exactly what I was wondering.
Okay, sure.
Other questions?
I have a kind of a basic question. When you talk about the electron heating versus ion heating, are you basically talking about a purely proton-electron plasma, or do the metals play an important role here? And I guess the follow-up question to that is, if they are, my understanding was that the ionization state and ion temperature was sort of frozen in the corona in the case of the solar wind, and that there wasn't a lot of development of that as it progressed throughout the heliosphere. So am I mistaken about that, or are the metals not an important part?
The metals certainly are an important part, and I left them out basically just for simplicity. So I guess you could go through the same type of argument about the thermodynamics and these different points in the turbulent cascade. And if you added in metals, then you get lots of different scales and different heating ratios for these different quantities. So basically you could have, for instance, if you imagine it depends on, say, the gyrators, you might expect to heat your alpha particles even more than the protons, and maybe iron or something even more than that. I'm actually not 100% sure what the amount of different heating we can measure on that is. There's some really nice work by Justin Casper showing that the heating of minor ions can be, or metals can be, much larger than expected in the solar wind, I think. So it kind of plays into the same type of thing, and I guess I was just doing it to be more simple. But yeah, it will all be determined by the turbulence and other things, if that provides some answer.
Okay, thanks.
So I have a quick question. You mentioned about, in particular, for the low beta case, the outcome depends on the mode of like the driving of the turbulence, like whether it's directional or it's like completely like randomized. So if I usually think of like the source of some sort of like compressive motion in astrophysics, I usually always think about like one directional motion. So like, can you comment on like astrophysical or like other examples that could be less directional, so like completely randomized?
Yeah, so I guess that was actually part of my point, is that most examples you do think of are directional. So if we want to understand things like the heating, then maybe, unfortunately or fortunately, depending on your perspective, you have to worry about that. Examples that might not be directional, well, in say the ISM, if you think that your turbulence is stirred by, say, a supernova going off, then that's probably somewhat adirectional in the sense that things will break up and eventually become so random that they're likely to not be strongly imbalanced. The strongly imbalanced case, like the solar wind, usually comes from when you have a big source in one region and then fluctuations that propagate outwards. So things like a corona are the obvious examples. So in the ISM, I think we don't really know, to be honest, what, say, the imbalance would be. And then so that means we can't really answer questions about these heating things at the moment. But you would expect probably regions where it's one, regions where it's the other, and sort of randomly across space. In detail, I don't know that we have any real prospect of measuring this, unfortunately. Yeah.
Okay. Other questions? If not, let's thank Jono. And for students, I believe students are meeting with Jono in about 15 minutes. So other than that, let's thank Jono for a very nice talk. And I'll clap for everyone.
Thanks, Jono.